Welcome to standard electrode potentials. So, the cell potential of a galvanic cell is the combination of our two electrodes. So we have two half reactions going on, and our total cell potential is the combination of these two potentials for our two half cells. So it's not possible to measure the contribution from one electrode, just like we couldn't measure, say, the ionic strength of just a cation without an anion around. We can't measure our contribution from just one electrode without some other electrode around, because we need both sides. We need both a cation and an anion. So, cathode and an anode. But we can define the potential of one electrode as 0, and then assign relative values to all the other ones. So we do the same thing as what we did with the case of ionic strength. With ionic strength, we defined the hydrogen ion to be 0, and then we measured all the others relative to that. We're going to do the same thing here, and we're going to pick a pretty equivalent case. We have the standard hydrogen electrode, which is sometimes abbreviated SHE. So here we have a platinum rod, so platinum electrode, solid platinum, and we have hydrogen gas that's being bubbled through. We're turning that into hydrogen ions. So is this an oxidation or a reduction step? That's an oxidation, right? We're removing electrons from our hydrogen. We're going to the right in our cell notation. We're moving this way. So note here that the platinum, the lines represent differences in phases. So in this case, the platinum isn't reacting to anything. It's just sitting there. It's allowing us to pass electrons from the other part of the cell over to this part to react with our hydrogen. We're removing electrons from our hydrogen to give us hydrogen ions. And note that we're defining our cell potential here as 0. It's not really 0, but we don't know what it is. So we're just going to say that it's 0 and measure the others relative to this one. So we're defining it to be 0 at all temperatures. So at standard conditions, the activity of the hydrogen ion is the activity of the hydrogen ions must be 1, which means we have a pH of 0. This is awfully acidic. And our pressure, our fugacity of our hydrogen gas must be at 1 bar. So our standard potential, so E naught, is assigned by constructing a cell in which the right-hand electrode, where the reduction is occurring, and the constructing a cell in which it's the right-hand electrode and the standard hydrogen electrode is the left-hand electrode. So let's look at an example. So if we have our hydrogen electrode, where we have hydrogen gas giving us hydrogen ions, or acid in this case, and silver chloride reacting to give us silver. So here, silver starts out with a +1 charge, and it ends up going to a charge of 0. So the silver is being reduced, the hydrogen is being oxidized. And so if we want to write our chemical reaction from this, we have half of a hydrogen gas molecule plus silver chloride gives us hydrochloric acid plus silver solid, elemental silver. And in this case, then we can say that the E cell naught is equal to E naught of this reaction. So the right side, the reduction side here. So we have silver chloride reacting to give us silver and chloride ions, minus the standard cell potential, so E naught, of the standard hydrogen electrode. This value we know is 1. Not 1, 0. And so that means that if this term is 0, that it goes away, and that means that whatever value we actually measure, that's all from, or we're saying it's all from the other half cell, right, our reduction cell. So that now turns our Nernst equation into this. So note over here on the right side, we've replaced our value of Q. So instead of natural log of Q, we've got this fraction So we have the activity of hydrogen ion times the activity of chloride ion divided by the activity of hydrogen. And note that it's raised, hydrogen gas, it's raised to a power of 1/2, so we're taking the square root here. So for simplicity's sake, we're going to write something. We're going to write this value. We're going to take this and set the fugacity here equal to 1. So when we square it, or when we take the square root, it's still 1. And we're now going to write this value. Sorry, what's missing in here is we're going to write this whole term, everything here. We're going to write that just as E0, just to make things simpler. And then we've cleaned up this this fraction a little bit. So if we express our activities in terms of molality B of hydrochloric acid, then we get our activity coefficients here in terms of molality. And again, remember we've got our activity coefficients there for both the cation and the anion. And that now makes our equation look like this. And so now we have a natural log term of involving the molality, and we have a natural log term involving the activity coefficient here. And now we can rearrange this, and so move the molality term to the other side. And then from our Debye-Huckel limiting law for a 1,1 electrolyte, so a positive 1, negative 1 electrolyte, we know that this is true. So we know that the natural log of our activity coefficient is proportional to the opposite of the square root of our molality term there. And now, if our proportionality constant for that equation is written like this, so Faraday's constant over 2 times R times the temperature times C, that means that now we can write this term. And so now I've just put that up here again. And so now on the left side, we can plot against this molality term, the square root of our molality divided by B0. Remember, B0 is 1 molal. And then extrapolate that. So we've plotted some data here, and we can extrapolate that down to a value for that term of 0. And our intercept here at 0 is the value for E0, so our standard cell potential for the silver chloride electrode. Right, so in this case, it's around 0.223. So note that the standard potential of a cell or an electrode is not changed if our chemical equation for our cell reaction or half cell reaction is multiplied by some numerical factor. So instead of having 1 mole of our reaction go on, if we have 2 moles of our reaction go on, the voltage is still the same, right? Our standard cell potential is still the same. Know that this numerical factor is increasing the standard Gibbs energy of reaction, but it also increases the number of electrons that are transferred by that same factor. And this means that the cell potential is an intensive property. So it doesn't matter how big of a cell we make, that voltage drop is always the same. Now, how many electrons we can get out, so the power of the cell, well, that will be different. But the voltage difference is the same. We can get more electrons out of a larger cell. We have more of our reactant around. But the voltage drop is the same. So, if we want to be able to get a battery with a really big voltage drop, we can't just make a really big battery. We have to stack cells together. So, for for two redox couples, so having some species, OX1, being reduced to turn into Read1, and OX2 being reduced to turn into Rid2, then our cell notation looks something like this. So again, we're moving to the right. So we have Read1 turning into OX1, and we have Rid2 turning into OX2. So, that means that we're going from our reduced species to the oxidized species here, and we're going from our reduced species to the oxidized species there. So, in this case, now we have our standard cell potential is equal to the standard potential for this part of the reaction minus the standard potential for that part of the reaction. And our overall cell reaction, note that this is not written correctly. We need to have here OX2 bar Rid2. So note that if we had it the way that I actually have it written on the slide, we're going from a reduction to an oxidation, from a reduced species to an oxidized species, so we have to remove electrons, and we're also removing electrons here. But we can't do that. So what we have to do is take the electrons away from this species and add them to this species. Well, when we add them to this one, we're making the reduced form. And so note here that that this guy, E1 naught, we're always measuring the reduction. But we're not reducing species 1. We're oxidizing species 1. Which means we have the opposite reaction. Right? And so when we have the opposite reaction, that means we're flipping our reaction around. We have to flip the sign on our cell potential, the cell potential for that half cell of the reaction. So overall, we have species 1 going from its reduced form to its oxidized form. We have species 2 going from its oxidized form to its reduced form. And now our reaction has a K, an equilibrium constant that's greater than 1 if the cell potential is greater than 0. So what does it mean for K to be greater than 1? Well, if K is greater than 1, then we have more products than we have reactants, and that means that the reaction should be spontaneous. And so if that's true, then spontaneous reactions then have cell potentials that are greater than 0, positive cell potentials. So a positive cell potential means the reaction is spontaneous. The negative cell potential means that the reaction is non-spontaneous. We're going to have to put in energy to get this to go. So if E cell naught is greater than 0, then that means that E2 naught is bigger than E1 naught. And this means that our reduced species 1 has a thermodynamic tendency to reduce our oxidized species 2. Which means low potential reduces high potential. So, in this way we can compare electrochemical potentials of various reactions, various half cells, and we can make an electrochemical series, arranging our elements in order of their reducing power as measured by their standard potentials in aqueous solution. So here we have table 6.3. I'm not sure whether you can read this or not, but we start out. This is of the metals, by the way. So we start out with the least strongly reducing, so the most oxidizing, and we end up going down to the most strongly reducing, so the least oxidizing. So we start out up here with gold and platinum, silver, and mercury, and we end up down here with magnesium, sodium, calcium, and potassium. Note that hydrogen is this point here, not metal, but that's the position of the standard hydrogen electrode in our series. So note that this series only determines the thermodynamic driving force, or lack of it, for a reaction. It doesn't determine the rate of the reaction. our reaction may be kinetically limited. All thermodynamics is talking about is which direction will the reaction proceed. It doesn't say anything about how fast it will proceed. The reaction may take longer than our lifetime. It may take longer than the lifetime of the Earth, but it will still proceed in that direction. The rate of reaction, how fast the reaction goes, is the domain of kinetics, not thermodynamics. Thermodynamics just says which direction does the reaction go. That's all it says. So, if we know our standard potential of an electrode in a cell, we can then use it to determine the mean activity coefficients by measuring the cell potential with our ions at our concentration of interest. So, for example, we can continue our earlier example involving hydrochloric acid, and that's at some molality B. And so now we have our activity coefficient, gamma plus minus, is equal to the cell potential, the standard cell potential, so E naught minus E cell, divided by this big term, minus the natural log of our molality term, so the molality divided by 1 molal, E naught. So if we know the standard potentials of our two electrodes forming a cell, then we can calculate the standard potential of our cell. So we have the standard potential of our cell, so at standard conditions, that's equal to the standard potential of the right portion of the cell minus the standard potential of the left portion of the cell. Again, remember that this value is for the reduction, but we don't have reduction on the left-hand side. We have oxidation occurring on the left-hand side, and so we have to subtract the value here. So, again, remember that we have this equation. So we have minus V is the stoichiometric coefficient, telling us how many electrons are transferred, times F is the Faraday constant, times E cell naught, that's the standard cell potential. That's equal to the standard Gibbs energy of reaction. And this means that if E cell naught is greater than 0, so if this value is positive, well then the left side has to be negative, which means the right side has to be negative. And that means that our standard Gibbs energy of reaction is negative. If standard Gibbs energy of reaction is negative, that means our value for K is greater than 1, because we have a spontaneous reaction if delta G is negative. If we have a spontaneous reaction, we should have an equilibrium constant that's bigger than 1. We should have more products than reactants at equilibrium. And so, now because we have this equation, that means that measuring our standard cell potential allows us to obtain our standard reaction Gibbs energy, delta RG. And so now, we can use the standard reaction Gibbs energy, delta RG, to calculate other thermodynamic functions, like the Gibbs energy of formation of ions, and this is explained more in Atkins section 3.6. So remember that the partial derivative of, or the change in Gibbs energy, G, with respect to temperature at constant pressure is minus S. And we know now that the standard cell potential is equal to minus delta RG naught over VF. And so we can combine these two to obtain the temperature coefficient of our standard cell potential. So how our cell potential is changing with respect to temperature. And so that now is so a slope of a plot of cell potential versus temperature would give us this slope. And so we have the standard entropy of reaction, standard entropy change for reaction, divided by V times F. So note here that this derivative is complete. It's not a partial derivative, right? It's not a partial derivative here, because our standard cell potential and the standard Gibbs energy are both independent of the pressure. And so it's an exact derivative. So now we can combine all of our results that we've obtained so far to obtain the standard reaction enthalpy. So standard reaction enthalpy, delta RH naught, is equal to delta R G naught plus T delta R S naught, which now we know is equal to this. So now we finally have a non-calorimetric method for determining the standard reaction enthalpy and then the standard enthalpies of formation of ions in solution. So that was standard electrode potentials.